The other type of actuator we're going to look at are rotary motors. These are similar to hydraulic motors in that they take our energy stored in our compressed fluid, in this case air, and it converts it into rotary motion with the amount of effort that is available measured as torque. Right? In terms of the amount of torque you can get out of a hydraulic motor, or I should say pneumatic motor, that's going to depend upon the size of the motor. Where larger motors are going to have larger areas, right? So areas where the fluid is sort of pressing on it, that's going to give us greater force that's converted over to greater torque. In addition, of course, you can increase the torque by increasing the air pressure. So those two things to take into consideration. In terms of the speed, that's going to depend upon flow rate and, of course, the size of the motor. Smaller motors have smaller internal chambers, and as a result, they need less air to make them move. Larger motors are going to have larger chambers, and usually we have sort of a trade-off here. If you want a high torque device, you're going to generally use a big device, but it's going to move relatively slowly. If you want a higher speed device, you're generally going to go smaller, and you go with a smaller volume inside. It's going to allow the device to move more, but you're going to get less torque out. Clearly, you can ramp up the pressure or ramp up the flow rate to change these as well. So in terms of the overall design, it's going to essentially work very similar to our motors and pumps in that we have to have an internal chamber that varies in size, right? So as the air comes in, it's got to expand. As the air goes out, it's got to compress or get smaller. In general, this is going to be formed by an outer housing, and then inside we're going to have a series of variety of different internal parts that rotate within a rotor, which is going to be attached to the output shaft that actually provides the power to the outside. In terms of the speed, as I mentioned, it's going to depend upon the size of the motor, specifically the displacement. Keep in mind when we talk about displacement, we generally think about motors displacement in terms of volume per time, so things like cubic feet per minute, because of the fact that we're dealing with compressible gas. And of course, the speed is going to increase or decrease depending on the volume flow rate that passes through the device. Torque is also going to depend upon the size of the motor. A larger internal structure gives us more effective area. And of course, we can increase the torque or decrease torque depending upon how much pressure we put into the motor as well. So in terms of the operation, we see a pretty standard setup right here where we have a series of vanes. This is a vane style motor. Air is going to come in, it's going to push here, it's going to expand this volume. As you can see in rotor position 2, the volume here is getting larger as the air pushes in, travels around, and then is pushed out on the other side. So this allows our motor to continue to rotate. Each time this goes around, we'll see if the vane's opening and closing to create these volumes. They're not really pumping chambers because that's really not the way the motor works. Kind of is the opposite. But it's a volume of pressurized fluid that's pushing this along. It turns out that we have a wide variety of pneumatic motor designs available, and that's because of the range of applications. Fact is, pneumatic motors are used in handheld tools, as those tools have to be relatively lightweight and small and portable. So in those cases, we're going to have lightweight materials and a very tight construction. Those do, however, generally are be relatively low power applications because size is somewhat connected to power. On the other hand, if we had an industrial use that required a high level of horsepower, this would be a much larger device. This is definitely going to be mounted down permanently to prevent torque and power issues and damage potentially to the device. So we'll see that we have designs that are available for this entire range. Clearly, whenever we talk about the design of a motor, we need to know how much air we're going to use. That's going to be connected to the speed. And of course, we need to know what pressure is going to be available. And that, of course, is going to be directly tied to the output torque, but it's also going to be connected to the design, the materials, etc. Let's start by discussing vane motors. Vane motors are the most common of all of our pneumatic rotary actuators. They can be scaled to be relatively small, as you can see in the diagram here. The person's using a pneumatic motor on a hand tool, but they also can be expanded up to large construction as well. That's one of the reasons why they're so widely used. They can be built with 3 or more vanes, 4 or 5, etc. number of vanes. And it turns out the more vanes you have, the less leakage you have. So that's one benefit, but the flip side is the more vanes you have, the more expensive the motor is, and there's the more vanes that are pushing on that outside edge, so the more friction they're going to generate. So in terms of your efficiencies, while more vanes gives us a higher volumetric efficiency, more vanes gives us a lower mechanical efficiency. So you need to kind of balance those two things out. In terms of the volumes inside the motor itself, the seal is going to be based on the vanes pushing on the outside housing or motor body. And of course, we want to make sure those vanes maintain that contact over a variety of motions and a variety of loads or pressures. How we accomplish that generally is below the vane, we either use springs to push out or we use air pressure. So we connect the bottom part of the vane to the high pressure side of the motor, and that air pressure pushes the vane out. So that's an effective way for maintaining those seals. As I said, there's a whole variety of different sizes available to down to a few inches in diameter up to feet in diameter, and they come in both lubricated or non-lubricated. That has a lot to do with how the seals are constructed inside. If it's metal to metal contact, you're generally going to have lubrication. If it's some other material that makes up the vanes, you can get away with them being non-lubricated. Another option in terms of our motors are piston motors. These tend to be used whenever we want a high level of torque or high power output that you cannot get necessarily from a vane motor. Just like hydraulic motors, they come in both axial or radial designs. We see an axial one shown over here, where we have a series of pistons going around in a barrel. We use a plate to open and close the various pistons. And of course, this whole thing is going to be attached to a power output. We use a swash plate that the pistons ride on to create that reciprocating motion. Right? Referred to as axial motors because the center lines of the output shaft and the pistons are aligned. Radial piston motors, on the other hand, the pistons are aligned in a radial pattern, essentially around the center line. Axial pistons tend to be somewhat larger. Radial pistons tend to be smaller, but usually capable of handling higher pressure. Now, there's a wide variety of different piston motors available. They can be as small as 1 horsepower or up to very large devices of over 50 horsepower. So we get a lot of power options available. And just like our other motors, these can be non-lubricated or lubricated, and mostly that depends upon the seal material. That the seal material, is it going to require lubrication for it to function long term, or is it going to be able to withstand the motion without any additional lubrication added? Last of the motors we're going to look at are turbine motors. Turbine motors use a turbine wheel, right? You can see it right here in this diagram. This is essentially similar to a non-positive displacement compressor or non-positive displacement motor, and what these are designed to do is mostly to operate at very high speeds, not high torques, but high speeds. And essentially, they work by having a nozzle deliver air right into the turbine, and the nozzle is going to convert the high pressure air into high speed air to move this turbine very quickly. As I said, it's generally going to be used for only high speed applications, not high torque applications, and generally going to be used with small devices, right? Because larger devices tend to need higher torque. An excellent example is this one right here. This is a grinder that we want to work at high speeds, but we're not really looking at high torque. terms of selecting your motor, again, we're going to go back to the specification tables provided by your manufacturer. Things they're going to tell you is how fast is it going to operate, how much power and torque you're going to get out, and as a result, how much air you're going to need to make this accomplish, how much air is consumed. Generally, we're going to show these in graphs because those things vary, right? Torque is going to depend upon pressure, so it's not going to be, tables aren't going to tell the whole story. So graphs are used to show the range of these values over their operating speeds. One of the key things we need to know is what type of loads we're going to be encountering. Generally, that's going to be in the form of torque, so what the maximum torque is. And you'll see tables like this shown below where you have a model. It's going to tell you speed, power, torque, its overall length and weight. So obviously this is something that you need to consider when putting it into a device or if it's going to be handheld. So now let's discuss some special application pneumatic actuators. First one I'm going to take a look at is known as pneumatic reciprocating motor. And calling it a motor is a bit of a misnomer because it actually is a form of linear actuator. What it's designed to do is to produce multiple cycles of linear motion. In fact, you can see an example of it shown over here. This is a jackhammer, or what's also known as a pavement breaker. And essentially what we want to have is multiple cycles of moving this tool up and down very quickly. We can do this a couple different ways. We can do it with what's referred to as percussive. In percussive, we actually have a piston that moves up and down freely. It's not connected to a rod, and essentially it bangs onto the tool at the bottom. This is designed to do a whole series of impacts on that tool at the bottom. Or we can have it connected with a rod, and that's referred to as non-percussive. But both of these are designed to do many cycles a minute, up to literally hundreds or even thousands of cycles, depending upon the device. In terms of our percussive one, we're going to have a cylinder with one end that's going to be closed off, and on the opposite end is actually going to be the tool, or what's referred to as the anvil. Things would be mounted to that anvil. Different tools could be mounted to that anvil, I should say. In terms of the cylinder itself, there's a free-floating piston that divides the chamber. We use air to push the piston down. When it strikes the end, we use that same air to push it back. But again, it's not connected with a rod. It's just that piston striking that anvil to transfer the energy. The other type of reciprocating motor available is known as non-percussive. This is not percussive because there's no impact involved. Instead, the piston has a rod attached. The rod extends outside the cylinder and is attached to the tool. And essentially, we're still using air to move it up and down. But in both cases, in both the percussive and non-percussive, the idea is that the motion is continuous. So as soon as the cylinder gets to its full travel, the valve opens and it moves back and forth. In terms of the control you have, you turn it on and off. And of course, you can oftentimes have an adjustable speed, but the motion itself is going to be continuous, constant reciprocating motion. Reciprocating motors are used in any application where you want a series of relatively quick reciprocating linear motion. So as I mentioned, jackhammers are pavement breakers used in building demolition and for breaking up pavement in streets. You see a scaling hammer here over the side. These are used to clean up welds and other fabrication material, for things like splatter from casting. We also use chipping hammers, very similar. These are going to be used on concrete surface for cleaning them up, or again, things like castings shown here on the right where we have rough material that we want to remove. They can be used in environments where we're using rivets, right, where we're shaping the heads of rivets. These are used in airplane construction. If we want to tamp down soil or sand, they can use for tampers or rammers. See here a foundry mold in a factory where we're tamping down the sand. They're also used in construction sites for, again, compressing new soil. So a wide variety of times, again, where we want that repeated linear motion to accomplish a task. In addition to the applications we've already discussed, it turns out that pneumatics are used in a whole variety of different equipment and various manufacturing and industrial processes. Generally, pneumatics is relatively inexpensive, so it's going to reduce costs, particularly if it improves on manpower and in terms of productivity. Generally, these can be small devices. Keep in mind, pneumatic, the whole pneumatic powered system, it can be relatively small, and to the point where they're widely available to consumers. Now many of those tools and techniques that were only available to large manufacturers in the past now can be purchased at home stores and can be available to the general public. Some areas where we see pneumatics used is various forms of spraying. For example, any type of painting is going to use pneumatics to apply the paint. We see an example here shown on the right where we use pneumatics to move fluids, in this case chemicals for controls of weeds, insects, putting down fertilizer, etc. If you need to dry anything in a chemical environment or at a car wash, we're going to use high pressure air to provide that quick drying process. We can also use compressed air to mix or stir a material. This type of agitation is usually designed to prevent solids from settling to the bottom if we want to maintain a uniform distribution throughout it. So things like sewer treatment plants definitely use it, but all sorts of also food manufacturing, beverages, etc. They use air for mixing the fluids. It's even used in the steel industry to agitate molten metals. We can also use it for moving various powders or granular material. So for example, if you need to move flour, a baker moving flour, air is used to carry that through a tubing system. It's used in other powder manufacturing like cement, etc., and used on very large scales for loading boats, cars, trucks, etc. Anytime you need to move a liquid, a powder, or any kind of granular material, you can use compressed air to expedite it, to speed up the process. Compressed air is also used to make a variety of different types of drills. Right? These are, again, linear impacts designed to drill holes in rocks. These can be done on a very large scale, as we see here, for example, in a mine or quarry, or potentially when we're looking at removing rock in a highway construction. This also can be done on a very small scale. So we actually have hand tools, pneumatic hand tools, that also can be used for drilling as well. A good example is in your dentist. A dentist's office actually has a whole pneumatic line, and that's what operates the dental drills. So we can see the scale can go from this massive machine down to something that's a fraction of an inch in size. Another device that uses compressed air to accomplish a variety of tasks are air nozzles. Air nozzles are pretty simple. They essentially are just a shaped opening which you put high pressure air through, and what it does is it takes that high pressure air and goes down to atmospheric, and it converts that air from the energy from pressure into velocity. We can have what's known as convergent or convergent divergent. This will speed up the air, and then slow it down a bit. And it turns out that we can control how that air comes out, specifically the velocity and pressure, by changing the various shapes of this nozzle. One of the areas where nozzles are used are with blowguns. These are in automotive shops and woodworking shops, etc., and designed to move debris and clean out tools. But it's essential to be extremely careful when using these. The fact is, it definitely may seem like you're just moving air around. The air is moving at a very high velocity. As a result, it can pick up debris and potentially get that into your eyes. So make sure whenever you're using them, you're using eye protection. The other issue is just the air itself. Since it's moving at such a high velocity, it can actually be injected right into your skin. So it's important to keep your your hands away from them, and of course never point a blowgun at anyone due to the potential to damage some of the more fragile parts of your bodies, particularly eyes and ears. Other areas where pneumatics are used are impact wrenches to loosen and tighten bolts. They are designed to provide high speed and impact to loosen up and move them, particularly bolts that may be stuck or corroded. Certainly, many of you may have seen them for mounting and removing tires, but there's a whole variety of different ranges of these available, from small scale up to very large scale. For example, they use them in the offshore wind industry, where they're putting down bolts that are, somewhere in the average of, say, 6 inches or even as much as a foot in terms of their cross-sectional dimension. Another area where pneumatics is used in nail drivers, or what's commonly referred to as nail guns. They're used in the construction industry for assembling furniture and all sorts of different type of carpentry applications. They can be used in building a home, but they're also so inexpensive, lightweight, etc., that they're commercially available and homeowners are using them regularly. There's a wide variety of fasteners available, things like large-headed nails for shingles or roofing, staples, very small brads, and up to very large nails, 2 inches or longer, used in the assembly of homes. Just like all the other devices, it's important to consider safety with these, and one of the key features that is definitely you want to make sure is functioning correctly on a nail gun is the safety feature where the nail gun has to be in contact with the material nail gun before it'll fire. We don't want that kind of safety measure to be restricted or not functioning correctly, because at that point then the nail gun can actually fire and the nails can come out as projectiles. Lastly, pneumatics is used in a wide variety of industrial applications. For example, here we show what's referred to as a gripper mechanism. This might be attached to a robot arm or a pick and place system, and it's designed to move or hold a part while some other function is going on, or to move it to another location. Fact is, with pneumatics, we can have a great deal of control on the force and on the positioning of these jaws. We can also use suction to pick parts up if we don't need as precise control. But the nice thing about this is they can be scaled to handle both small devices or very large devices, and they can be set to be extremely accurate, where we can set the process to be very repetitively come up with the exact same location, exact same opening, exact same force, etc. And pneumatics are particularly good at working with these types of devices. As with all the other stuff we covered, there's additional details in our textbook that you definitely want to be reading and covering in detail. There's more videos available on the course base. And as always, if you have additional questions, don't hesitate to get in touch with me.